These should happen at the same time. If you heard the beep before you saw the flash, make the bottom loop longer. If you heard the beep after you saw the flash, make the bottom loop shorter. If your projector is set, let's try it again. Your film is now ready to be shown.
I'm Bill Ryan. This is the Smithsonian. Behind me, in front of me, all around me, the Hall of Osteology. To many visitors, it's better known as the bone room. And all kinds of bones, small bones and big ones, short ones and long ones, skinny ones and thick ones. Bones used in flying or in swimming, bones used in jumping, in running, in walking, and in sitting. How many bones do you think we have in our bodies? The answer? Slightly over 200. In a baby, many bones first appear in several parts. Now, these parts fuse in regular fashion to form the single adult bone. Now, sometimes fusion is not complete and an extra bone results. Occasional accidents of development duplicate pairs of structures. For instance, about 1 person in 20 winds up with an extra pair of ribs. The arrangement and distribution of these bones reveals a precise and intricate pattern. 29 in the skull, many of them interlocked at the edges to give protection to the brain, and thick compared to the delicate bones of the face. 26 vertebrae in the spine, and 29 rib bones. On the upper half of the spine, the shoulder girdle supporting the arms, and on the lower half, the hip girdle supporting the legs. 30 bones in each arm, and all but 6 found in the wrist and hand. "30 bones, too, in each leg, and all but 8 found in the ankles and feet. About half of the bones in the body found where they will do the most good, in our hands and in our feet." Finally, bones are durable. They last long after the flesh and muscle that surrounded them are gone. And because they last, bones give us our best clue as to what life was long before we arrived on this planet. From the bones that remain, we can see creatures that no man ever saw walk the earth. Dinosaurs of prehistoric time, extinct millions of years before the first man. And yet, there's so much we know about them. We know, for instance, that there were two distinct types of dinosaurs, and the difference between them is found in the arrangement of their pelvic bones. As you can see, in one type, these bones of the pelvis were long and parallel to the backbone, while in the other, the bones were angled downward from the backbone and joined in a strong arch. In both types, there were those who walked on two legs and those that walked on all fours. Most of the four-legged dinosaurs were peaceable, plant-eating animals, as in the case of this fellow here, Stegosaurus. His teeth were small and weak, and obviously he fed upon vegetation that did not require cutting or chopping. A huge animal measuring almost 20 feet in length and standing 10 feet high. And with this recreation of Stegosaurus, we can see one of the most interesting features of this type of dinosaur, a series of bony triangular plates running down its back. No one knows for sure what function these plates served, protection perhaps, and certainly they did not make Stegosaurus look very appetizing to his meat-eating cousins. Were he to be attacked, however, Stegosaurus had a potent means of defense. A double pair of 24-inch spikes on his tail, which he could whip with deadly effect into the soft underbelly of an attacking enemy. The skull of Stegosaurus was extremely small in relation to the body, and it held a brain no bigger than an orange. While Stegosaurus was frightening enough, the real killers of prehistoric times were the two-legged meat-eaters like Ceratosaurus. Here, the forelimbs are shortened. We don't know why. While the hind legs, which carried the full weight of the creature, are greatly strengthened, with the long tail serving as a counterbalance to the body. Unlike the skull of the vegetation-eating dinosaurs, the head of the Ceratosaurus is large and equipped with long jaws and sharp, strong teeth. Combined with the large claws of the forelimbs, the Ceratosaurus becomes 3 or 4 tons of destructiveness. While the dinosaurs, like Ceratosaurus and Stegosaurus, ruled the land, other reptiles solved the problem of flight. From their bones, we can reconstruct these flying reptiles and find out that their wings consisted of a membrane supported by a tremendously lengthened 4th finger. The other fingers were hook-shaped so that the animals could hang from rocks or trees. Probably these airborne reptiles did not fly as much as they glided, for they lacked the powerful muscle system needed for really efficient flapping flight. In some of the reptiles, however, the wing area was huge. The pteranodon, for instance, had a wing spread of more than 20 feet, allowing it to soar on warm air currents for extended periods of time. While the great creatures of prehistoric time inhabited both the land and the air, still others returned from where they'd come, the sea. With strong, thick backbones and powerful tails, they moved easily through the water. And although they continued to breathe air, these land adaptations became readapted for life in the sea. Limbs, for instance, either became flippers or disappeared completely, as we can see in the neatly streamlined skeleton of a gigantic lizard, 24 feet long, and in life probably weighing up to 4,500 pounds. From its skeleton, we can get a pretty good idea of what this 70 to 80 million year old reptile looked like. A record of our planet's history and the creatures who lived on it as seen through bones. But before we can see that picture, we must first find and preserve those bones. And that's an exciting scientific treasure hunt. Most of the animals of prehistoric times are gone, but their bones remain to guide the scientist in reconstructing what life was like millions of years before man. The bones are there, but first they must be found. This is what western Nebraska might have looked like some 20 million years ago. The climate was not too different from the present day, and even the plants are familiar. Willow, poplar, sumac, and various grasses. Animals related to modern horses. antelope, rhinoceros, camels and dogs were present, but of a form such as no man has ever seen. Then, for reasons no one really understands, they disappeared from this continent. But their bones remained, buried through millions of years. Seas and mountains and great masses of land came and went. The surface of the earth changed and rechanged, but the bones, embedded beneath ancient rock, waiting to give up their secrets, remained. Prehistoric bones are found in sedimentary rocks, sandstone, limestone, shale, as well as clay, and found in areas where erosion by wind and water has worn down the sediment and exposed the bones to view, such as here along the banks of the Potomac River. Ancient sediments are also found in places where, because of a shift in the Earth's strata, a long buried layer of rock or clay has been brought to the surface. When a layer of promising-looking material is found, in this case clay, it is patiently and carefully searched by the scientist. The search may go on for days and weeks and is a tough, tiring job. But then the reward, a specimen of fossil bone. He will probe the exposure to determine the extent of our find, and then start to dig away the clay over the specimen. Our scientist is Al Myrick of the Department of Vertebrate Paleontology at the Smithsonian. When most of the clay has been removed, he removes the remaining layer, the one just on top of the specimen, very carefully, using smaller instruments. Tools as small and delicate as those of a dentist, the clay near the bone is removed. Then, when the outlines of the specimens have been exposed, the excavation is enlarged and back cuts and undercuts are begun. Frequently, in blocking bone out, additional bone is found. Because of this possibility, extreme care must be taken. Until, at last, the bones are exposed in their centuries-old resting place. In dealing with individual bones in the field, great care must be taken to protect them. Once exposed to the air, they become extremely delicate, so they're encased in plaster casts to protect them from exposure and damage. Then pre-plastered gauze is used to jacket the specimen. And when the plaster has set, the specimen can be packed and shipped back to the museum laboratory. And the first thing to be done back here at the Smithsonian is to remove the protective plaster cast.
That's right, Bill. The first thing we'll do is to remove the jacket in order to reveal the bone and clay which it encases. Now, when that is sufficiently exposed, we will have something like this. This Miocene whale has already been partially prepared, and the first thing we'll do is to soften the matrix, which is now very hard, with alcohol, which evaporates readily and doesn't cause the bone to warp. Once the bone has been completely cleared of the matrix, a solution called Alvar is applied. It saturates the bone and strengthens it. Once the Alvar dries, the bone is ready to be stuck together and patched. For this, we use a substance called guck. Guck is made up of a combination of plaster, alvar, and asbestos. The alvar gives it the sticking power. The plaster will keep it from shrinking. The missing pieces are filled with guck, and in this case it will help to hold it together as well as showing more completeness to the bone. After all the patching is completed, the guck is then allowed to dry. It's smoothed off and painted a different color in order that we may be able to tell it from real bone. A specimen such as this may take as long as a year and involve perhaps 1,000 pieces, which we will take out, harden, and put back in place. A result may be something like this, Bill, a 20-million-year-old whale skull. When it is ready for study, we'll put it in a plaster cradle.
Mm-hmm. And happily, for those interested in finding fossil bones, America had an abundance of prehistoric animals, and their bones have been found from Connecticut to California. The Smithsonian, for instance, has fossil sites in western Maryland where this peccary came from. This one, still in preparation, is from Pennsylvania, and this early pronghorn is from Arizona. As a matter of fact, the Smithsonian has fossil sites in all 50 states. What are your chances of finding fossil bones? Well, pretty slim, I'm afraid. Fossil finding is often a discouraging proposition, even for experienced workers. Nevertheless, some important fossil discoveries have been made by amateurs. One of those peccaries was found by a teenager, and university students worked on excavating this prehistoric wolf and horse. And our whale fossil here was first found by a teenager. But one note of caution: carelessness or inexperience can destroy in a few seconds what has survived for millions of years. In your search for fossils, you might make a significant find. Contact your nearest university or museum. Someone there will tell you what it is, and you may well be making an important contribution to science. Bones. The role they play in telling us of the history of the Earth is a fascinating and never-ending story. But bones can also tell us much of the creatures who inhabit the world today: where and how they live, what they eat, how they're built, how they move. One of the most important sets of bones in the body is the spinal column, an arrangement of intricately jointed bones that gives the back its shape. There are 29 in nearly all mammals, including the tiger and us, but the number ranges from about a dozen in a turtle to more than 200 in some snakes. Strong yet flexible, the spinal column aids in support, balance, and motion in humans and in this cheetah. As the cat runs, for instance, the spinal column is flexed upward and downward, which by shortening and lengthening the body pushes it forward and extends its reach to new ground, where the process is repeated. But these are animals confined to the ground, and their spinal columns must also be used to fight against the downward pull of gravity. Now, birds must solve this problem in two very different ways: supporting their bodies while flying through the wings and shoulders, and while standing through the legs and pelvis. Bones of the pelvis fuse with vertebrae from the lower trunk, back, and tail to form a rigid support. The vertebrae supporting the rib cage are also often fused for additional support. The wings are used to propel the bird while gliding, also as brakes in landing, for support or flapping, or for hovering in place, as a hummingbird does. Unlike the body vertebrae, the neck vertebrae are designed for great versatility, allowing the bird to perform diverse tasks with its bill: feeding, nest building, protection, and feather care. Most of the early aircraft designs used birds as their models. But the bird in flight was much more graceful. Just as the bone structure of a bird is shaped for flight, the skeleton of a fish is designed for movement through the dense medium of water. Now, while in birds, the backbone is stiff to give support to the wings, in fish, the backbone acts as a flexible rod to support the muscles used for swimming. The spinal column swings from side to side, and the fish moves forward by pushing part of its body and tail backward against the water. In snakes, who have more bones than anybody, we get some of the most curious of all motions. Now, all snakes can move forward in at least 3 different ways, and one of these is best illustrated by the boa constrictor. The boa can crawl straight ahead, the belly scales of the snake moving across the ground like the many legs of a caterpillar. Snakes also can move ahead using the snaky motion most people are familiar with, such as the Russell's viper. The snake gains traction as it moves from bumps in the ground, sticks, stones, and even blades of grass. Where it can gain no traction, a snake can use a type of accordion movement. The cottonmouth, for example, can stretch and contract his body like an accordion to move across the ground. The strangest of all snake movements can be seen in the Texas sidewinder. This unusual rattlesnake goes forward by seeming to thrust and loop his body in a sideways motion. He even appears to be rolling like a hoop. Actually, he lifts his head, throws it to the side, loops his body after it, and the tail follows as the next loop starts. The human skeleton, a marvelously designed structure equipped to do a variety of jobs. In all, the bones of the body are a masterpiece of form and function. So that while a gorilla is stronger, and a fish can swim faster, and a horse run further, and a kangaroo leap higher, only man can do so many things so well. The incredible functions of bones, shaping the architecture of the living body, and then remaining as clues to the past. The world changes. The mountains, the land, the ice, and the desert all change. And with each change, so do the creatures who inhabit the earth change. But by seeing and knowing and understanding the record they were in the past, what they are now, and perhaps what they will be in the future.